All right. So just as a reminder, that's a coefficient. What it means is that you have two magnesiums. And this one right here means you have two magnesium oxide. And this is a subscript, and it's just saying that your molecule looks like that. It doesn't tell you how many you're using for the reaction. It just tells you basically what it's like. You could kind of think of these as recipes. So you could think of it as like, trying to think. So you could think of it like, this wouldn't actually make anything, but you could say we have flour, and then eggs, and then, oh, Jackson, you have a question. Do you have a question, Jackson? Let me see if my volume is up. Yeah, it is. If you're talking, you may be on mute.
Oh, sorry. Yeah, I don't have a question.
Oh, okay. I was just checking to make sure.
No, I'm sorry about that. I was on mute.
No, that's all right. And then this one would be like, you make a cake. Obviously, that's not all you need to make a cake. This just is for an example. So the 2 right here is kind of like saying 2 cups. And then there's no coefficient here. So we know that the coefficient is 1. So, and that would be like 1 egg. And then here, the 2 would be basically saying that if you had 2 cups of flour and 1 egg, you get 2 cakes. And so that's what the coefficients are for, is to tell you how many of what make what. Now, we can think of it a couple of different ways. Put that back. All right. We can say that if you have 2 molecules of magnesium or not 2 molecules, 2 atoms of magnesium and 1 molecule of O2 and 2 formula units of MgO, then that would be what's required and what's made. Instead of molecules, you could say moles. Like if you had a mole of something, you could, multiply the whole thing by 1 mole. And then that's basically saying for every 2 moles of magnesium, you're going to need 1 mole of oxygen, and you'll produce 2 moles of magnesium oxide. So that's what we're going to use, and that makes them useful because you can use them as conversion factors. So you could have 2 magnesium equals 1 oxygen. It could be like 2 moles. Or you could have 1 mole of O2 equals 2 moles of MgO, and so forth. You could also, instead of saying moles, you could say for every 2 magnesium atoms, you need 1 O2 molecule. Something like that. Or you could say 1 O2 molecule equals 2 MgO formula units. So those help you convert. You can convert from, this should have been a capital M there. That's a good question. That's because with Mg, there's no subscript. So we know there's just 1 of them. So then that would have to be an atom. With O2, the oxygen are stuck together. This is obviously not the right Lewis structure, but the oxygens are stuck together by a covalent bond. And so here we're saying that there are two things, two atoms. So we will call that a molecule because they're stuck together. And then this one is called a formula unit because it's ionic. It basically means the same thing as molecule, except when you use the word formula unit, you're saying that this, whatever it is ionic. All right, so let's do an example. Let's see. You should be able to know whether or not it's an atom, molecule, or formula unit. That's not going to be my main thing for you guys to focus on. It's just, it is a good thing to know. But for this one, the main thing that I'll be focusing on is conversions. But there may be a question in there about, which one is a formula unit or which one is a molecule. But I'm not going to have the whole test riddled with, molecules, formula units, and all that kind of thing. You're welcome. All right, so let's take a look at an example. Let's use this one. All right, so for this one, we're just doing combustion of a hydrocarbon. So the hydrocarbon is C8H18. And so that's making carbon dioxide and water, as it always does. So we balanced, I think we actually balanced this. If we didn't balance this, we balanced something really similar to it on Tuesday. So that's the first thing you want to check, is you want to check and see whether or not the equation is balanced. If you don't see any coefficients, most likely it's not balanced. But if you see a lot of coefficients, it's most likely balanced. So some equations they give you will be balanced and others won't be. So we're going to start off with a balanced one and just kind of go through an example. So let's say we have 3.7 times 10 to the 15th grams of C8H18, so octane, and we want to know how much carbon dioxide is produced. The first thing to remember is you can't go from grams of one element or compound to grams of another compound. You can only go moles of a compound to moles of a different compound. So anytime you see grams here and grams here, that means there's going to be a middle step somewhere where there's moles to moles. So here we're going to go grams of C8H18 to moles of C8H18 to grams, or no, to moles of CO2 to grams of CO2. And each one of these arrows is going to represent a step. So if I was to draw my little thing here, I have 3 arrows, so I'm going to have 3 steps, so I need to have 3 sections. And to begin with, we're just going to write down the information they gave us. So they gave us 3.7 times 10 to the 15th grams of C, or of octane. It's important to put what it's grams of, because you can see here they're talking about octane, but in the end they want to go to carbon dioxide. So you need to write down what it is you have, because this one is not terribly long. You just go from one thing to another. But as they get more and more complex, they kind of take a turn, and it helps just to have as much information as you can as you go through it, even though it takes a little longer to do it. So if I'm going to go from grams to moles, what do I use? Any ideas? Molar mass. Cool. Good. And to get molar mass of octane, it's 8 atoms times 12.01, and then 1 atom times 1.007. And then that gives us a molar mass of, let's say, 114-ish. Oh yeah, 18. Why did I do 1? I was looking at that going, that doesn't equal that. Okay, so I'm assuming if you put this in your calculator, actually somebody put it in your calculator and tell me what you get. Thinking it's around 114 because that's what I have in my notes, but that doesn't mean I have it right. So 8 times 12 is like 96. It's 18. 114. Okay, good. Now, why did I choose to put the grams on the bottom? Right, so I can cancel it out. If I have 1 on the top and 1 on the bottom, they'll cancel out. All right, so my next step is to go from moles of octane to moles of carbon dioxide. So that's this step here. So what do I use to go from moles of one thing to moles of another? This is the new step that we haven't used before. Coefficients. Excellent. Yeah, so we're going to use our balanced equation and use the coefficients from our balanced equation. So octane is on the top here, so I'm going to put it on the bottom here. And then I'm trying to go to carbon dioxide. Okay. And to figure out how many moles of what, I'm going to look up to my balanced equation. Here's carbon dioxide, and the number next to it is 16. So I'm going to put a 16 right here. And the number next to octane is 2. So I'm going to put a 2 right there. And then oh, I screwed this up. So, I mean, this is correct, but when I told you there have to be 3 sections, that would be 3 steps. This is just where you write down what you're given. So, sorry about that. Okay. So, then the next part is to go from moles to grams, and what do we use to go moles to grams? Right, molar mass of CO2. And what is the molar mass of CO2? Yeah, so we're getting 32 and 12, 42, 44. Look, that goes on top. That is okay. All right. So now all we have to do is plug it into our calculator. So the easiest way to do this is to go and multiply everything across the top, making sure that if you have anything like this, you've got parentheses around it. And at the bottom, so then that's going to give you an answer on the top. And then on the bottom, you're going to multiply those things and then get that answer and then divide them. So what do we get at the top when we multiply all that stuff across? So that'd be 3.7 times 10 to the 15th times 1 times 16 times 44. Let me see if I can pull up a calculator. to rearrange all these little icons on my phone. Okay, cool. Thank you, Josh. So 2.6048 times 10 to the 18th. And what do we get for the bottom? 228. And then when we divide them, what do we get? All right. 4? Is that right? Does everybody get 4? $1.14. Anybody else get 1.14? Okay. Yeah. Just make you didn't. Okay. Let's see. Let me find a calculator that is assigned to calculator. I have this phone. There we go. Okay. So what we're going to do, we're going to put it in the calculator. I'm going to put it at the top. I'm going to put it in calculator. Parentheses, 2.6, what did I write there? 6048 times 10, and then the little caret symbol, and then 18, and then the divided by symbol, and then 228. Okay, all right. Let me put it in my calculator and see what I get. Good. Okay, you got it. All right, cool. So then that's the answer is 1.14 times 10 to the 16th. And that would be grams of CO2. All right. Yes. You just do them one at a time. There is no space on the board anymore. Yeah, if I didn't have different colors, we wouldn't be able to read a thing. You can hardly read what's up there. But yeah, you want to do them one at a time. An alternative method is to put this in your calculator and then hit enter and then use it as an answer. And then, so you put this in the calculator, click enter, and then answer times this, enter, answer times this, enter, and so forth, like that. Okay, let's take a look at another one. Let's see. Assuming I can find my cursor. Where is it? Okay, there it is. Try to look for a good one. That was sort of okay. Ah, okay. We'll get to that one in just a second. All right. Yeah, that one was given in the problem. All right. So let's say we have this equation. And let's see, we've got 2 SO2, sulfur dioxide, plus 1 O2 makes, no, not makes, that should be plus, plus 2 waters, makes 2 H2SO4. All right, so that would be sulfuric acid. And in the problem, it gives us that we have 25 kilograms of SO2. We'll put that in blue. And then it wants to know how many kilograms of sulfuric acid. So there are Couple of things. The first thing is to kind of map your way through it. Now, we know that if we're going sulfuric acid, well, sulfur dioxide to sulfuric acid, do we do grams to grams, moles to moles, kilograms to kilograms? How do we get from one to the other? Correct. Caspian is right. And then Hunter's right. Yep, Josh is right. So we're going to go kilograms of SO2 to grams of SO2 to moles of SO2 to moles of sulfuric acid to grams of sulfuric acid to kilograms of sulfuric acid. All right. That's just kind of long. Told you sometimes they get a little bit long. All right. So for this one, just to save time, I'm just going to give you the molar masses. But the molar masses that we use, we're just getting them from the periodic table. So for sulfur dioxide, it's going to be 1 times sulfur's molar mass plus 2 times oxygen's molar mass. And then the answer there would give you the molar mass of the compound. So we're going to start out with 25 kilograms of SO2. And we're going to go to grams of SO2. I hate it when I put those lines in it. It drives me absolutely bonkers. I'm not sure exactly why they show up. I think it's because of where I put my hand. Okay. We'll just ignore the part at the top. All right. On artistic style, yeah. It would be an example of that. Okay, so how many grams in a kilogram? Oh no, somebody did it, made it go back. That's so sad. Correct. All right, so what are we going to have on the bottom? The grams or the kilograms? Correct, the kilograms, because I have kilograms on top, so I want kilograms on bottom. All right, so that is going to be 1 kilogram of SO2 is 1,000 grams of SO2. All right, so we've done this part. All right, so now we want to do the next piece, which would be this one, going from grams to moles. So how do we go from grams to moles? The molar mass, good. So we'll use the molar mass of sulfur dioxide. And so we're going to have grams of SO2 on the bottom and moles of SO2 on the top. The molar mass of sulfur dioxide is 64.07. So it's grams per how many moles? 1, correct. So when you're going grams to moles, moles always gets the 1. All right, so we've done that step. Now we're going to do the new step that we are learning, which is moles of one thing to moles of something else. So for that, we're going to use coefficients. All right, since I have sulfur dioxide moles on the top, I want them on the bottom. And then I want moles of H2SO4. And I know I want moles of H2SO4 because that's given, that's the question, right? So it's asking me how many kilograms of H2SO4. You could, I'm only showing it because just to kind of give you the method in case you run across one that's not 2 to 2. But yes, since it's 2 to 2, that's just a 1 to 1 ratio. So you can just kind of skip over. It's always better to show all the steps, but in this case, it literally is just multiplying by 1. So if we're looking at sulfur dioxide right here, its coefficient is 2. Not sulfur dioxide, sulfuric acid. And then sulfur dioxide right here also has a 2. And obviously 2 divided by 2 is just 1. So that doesn't really do much to the number. All right, so now let's do gray for this step. So we're going to go moles to grams. So that's going to be molar mass again. I'm going to shift it down a little bit because I got my kilogram in the way there. And so it's going to be moles H2SO4 to grams H2SO4. And using the molar mass of sulfuric acid, it's 98.09. And it's going to be per 1 mole. And then the very last step is just going to be this one right here, where we go grams to kilograms. And we're going to use that 1,000 grams equals 1 kilogram. All right. Can you guys see that? Isn't that green? Yes. Okay, good. So we're going to multiply across the top. It's going to be 25 times 1,000 times 1 times 2 times 98.09 times 1. Obviously, the 1 and the 1 just leave out. And then we're going to divide that answer by 1 times 64.07 times 2 times 1. And since we have a 2 on the top here and a 2 on the bottom, those really just cancel each other out. So you could leave them out, or you could put them in. In the end, you're going to get the same answer either way. And you want to have this in parentheses and that in parentheses so that they do the right thing. Oh, yeah, times 1,000. Well, divided by 1,000 on the bottom. Yeah, so 2 times 1 times 1,000. Thank you. That was going to give me a weird number, wouldn't it? Okay. Let me fix that a little bit. All right. So 38.27. Yep. All right. So if we start out with 25 kilograms of sulfur dioxide, if everything goes the way it's supposed to in the reaction, we would get 38 kilograms of sulfuric acid. Now here's a question. If I start out with 25 kilograms here, where do I get the rest of it to get the 38 kilograms? Correct, the oxygen and the water. So obviously there is some amount of this and some amount of that that also goes into the reaction as well. And so when you add all that together, then you'll get the 38.27 grams. Or not grams, kilograms. That brings me to another point. Does anybody need a second on this page? No? Okay. So there's the law of conservation of matter. That's why we balance the equations. And there's also the law of conservation of mass. So if on the left we start out with 83 grams, then on the right we should end up with 83 grams. So just so you know, in the end, they should, equal. Let's see. That's a good question. That is because you end up with H2SO4. Oh, what you're saying is, how would I know if I was writing it out that there was water and oxygen? Is that what you're saying? At this point, you probably wouldn't, but once you get used to it's in this case it's just the case of memorizing. We obviously know there's something with hydrogen and something with oxygen, but there are a lot of different options. You could have hydrogen peroxide, you could have water, you could have H2 and O2. So there's a bunch of different things that you could have in there, and you don't really know. So in the end, it's just kind of like memorizing it. This isn't necessarily one that you would know immediately right off the top of your head. The combustion for NH3. I am thinking, did it not give you any more information than just what's the combustion for NH3? Huh. Interesting. All right, I'll have to take a look at that, and I'll send you guys out some information on those to kind of guide you through those. Because I don't, off the top of my head, I don't know what NH3 makes. I know. No, I'm thinking ammonium. Yeah, probably. I haven't worked with that one in a while. I know we used to do an experiment that had the magnesium oxide experiment. You also have side reaction with nitrogen, but that's just nitrogen and not ammonia. So I haven't done that one in a while. Oh, that one I'll actually have to look up. The only thing that I could think is that, let's see. No, I don't even think that. I was gonna say the only thing I could think is that maybe it's a gas reaction. Well, it could be a gas reaction. There are certain gas reactions that you have to memorize. You can just look those up by going to Google and typing in gas reactions or common gas reactions, and it'll show you the various types. And ammonia is a gas. Okay, this is a question where we're reacting 2 molecules of nitrogen gas with 6 molecules of hydrogen gas to form. Oh, if that's the case, then it's just telling you the problem. Okay, yeah, that makes sense. It sounds like the question is kind of giving you the starting point, and then you've got to balance it. The main things that you've got to know in that case would be that nitrogen gas is diatomic, and that hydrogen gas is diatomic, and that ammonia is NH3. Let's see what we get. So what was it? Nitrogen plus oxygen makes NH3. Obviously, there's going to be hydrogen in there somewhere. Nitrogen, 6 hydrogen. Oh, there's no oxygen at all. Okay. I'm doing it again. All right, so it would be 1, 3, and 2 for the coefficients there. Oh, don't put 0 for nitrogen. You want to put a 1 for nitrogen instead of 0. It's tempting to put the 0. It's just kind of like when you see x plus x, you know it's not 0x plus 0x because that would just be 0. It's 1x plus 1x equals 2x. Oh, okay. How many molecules are in the product? Okay, yeah, no, that makes sense. That does make sense. All right, I actually have to take an actual look at the question. All right, so let's take a look at trying to figure out how much we need to make a certain amount. So we're going to be looking at limiting reactant. And there are some more examples in the notes there if you want to, if you need a little bit more practice. There are some examples and some, explanations there. So let's see. All right, so now I'm on page 7 of the notes. We're going to limiting reactant and percent yield. The limiting reactant is the thing that's used at first. Well, reactant. For example, let's say I have 9 slices of bread, 4 slices of cheese, and a sandwich is 2 slices of bread and 1 slice of cheese. If that's the case, then I can figure out how many sandwiches can I make. So how many sandwiches can I make if I have 9 slices of bread and 4 slices of cheese? Correct, I can make 4. Which one am I going to run out of first? The cheese, correct. So the cheese in this case would be the limiting reactant because I run out. So I could say, well, I've got 9 slices of bread. We'll just do 9B for bread. And I want to know how many sandwiches I would get. Or better yet, we could balance the equation of sandwiches and bread. This is pain in the behind. Okay. All right. So we've got bread plus cheese makes, and let's say B2, because you have to have 2 breads each time, makes a sandwich, which is B2C. In this case, everything's kind of balanced, but we know that with bread there are 2. I think it'd make more sense to do it this way. Yeah, I like that better. Okay. So if that's the case, if I have 9 slices of bread, I don't know how many sandwiches I can make. Well, I know 2 slices of bread makes 1 sandwich. So that'd be 4.5. And then I could do the cheese part over here. And so if I have 4 slices of cheese, I know from here that 1 slice of cheese will make 1 sandwich. So the most I could make with the cheese is 4. So if I only have enough cheese to make 4 sandwiches, obviously I can't make 4.5 sandwiches. I can only make 4. So that's limiting reactant because it's the one that makes the least. It's the one that runs out first. All right, so let's do a really simple example for that. So we're going to do our methane combustion. Four would be the theoretical yield. That is correct. All right, so methane plus oxygen makes carbon dioxide and water. All right, that works. So let's say I have 5 moles of CH4 and I have 8 moles of O2. Then I want to know 2 things. Which one is the limiting reactant? and then how much of a product could I get? If they don't specify which product and they just say, okay, which one is the limiting reactant, then you're just going to say, well, my methane could make a certain amount of water, or my methane also makes a certain amount of carbon dioxide. So I can pick either one of those products to stick to kind of represent like sandwiches. This is kind of like the bread, the cheese, and the sandwich. Or if I wanted to, instead of using CO2, I could use the water. It doesn't matter, but whichever one I pick, I have to stick with it. So I have 5 moles of methane, and for every 1 mole of methane, I produce 1 mole of CO2. All right. So that's 5 times 1 divided by 1 is 5 moles of CO2. And this part right here, I'm getting from the coefficients of these two things. Since you don't see one, it's coefficient of 1. All right. And the next one is 8 moles of oxygen. Looking at the coefficient for oxygen, it's coefficient of 2. And for carbon dioxide, it's 1. All right. What is the most carbon dioxide I can make with these ingredients? 4. All right. And which one will have some left over? That'll be the CH4. So this is called excess. And this is called limiting reactant. Note, there's one important thing to note, is that we started off with what looks like less methane and what looks like more oxygen. But that's not, you can't just go by the fact that we have 5 of one and 8 of the other to decide without any math which one is the limiting reactant. You have to do the math, because in this case, the one that had 8 moles was the limiting reactant, as opposed to the one that has less moles to start with produced more carbon dioxide. Right? But this would have worked just as easy to tell me the answer as to which one is the limiting reactant had I used water instead of carbon dioxide. The main thing is I have to pick either carbon dioxide or water. I can't do like carbon dioxide here and water there, because it wouldn't give me a good relationship. All right. So let's take a look at a more complicated one. Let's see how much time we've got. Oh, 3 whole minutes. Yeah, I'll just briefly go over theoretical yield. There is an example on page 8, if you need to look at one, on how to go through a limiting reactant problem and how to get theoretical yield. And then there's percent yield problems there also. Yeah, you could do either CO2 or H2. All right, so actual is the amount that comes from the real experiment. Theoretical is the amount from math. And percent yield obviously would be the percent of the product formed compared to what you theoretically could. So for example, let's say I'm making let's say I'm doing the sandwich thing. I got 9 slices of bread, 4 slices of cheese. Theoretically, I can make 4 sandwiches. Let's say partway through making my sandwiches, my dog jumps up and licks one of the slices of cheese. So unlikely I'm going to make 4 sandwiches from that, right? I would end up being, oh, it's 11 o'clock. So, oh, that's so fun. Well, that's all I've got. No, isn't that weird? It's like, what's up? All right. So that's all I've got for today. We'll finish up this and start new stuff on Monday. And it is weird. We'll see you guys Monday.